Okay, so what happened last time, quick recap, is in one sentence, we saw, or at least I sketched the pictures that go along with the formal arguments of how you go from an Anosov flow on a three-manifold to an action, well, to a plane with transverse foliations which I think I was calling the induced from unstable and stable, and an action of the fundamental group on this plane, preserving these foliations by homeomorphisms. Actually, this plane inherits a smooth structure if everything was smooth to begin with, and you had a genuine Anosov flow. And this action is by Diffeomorphisms, or at least, sorry, it has a C1 structure. But I don't really know how to use that to my advantage, and in the pseudo-Anosov case, you don't generally have that. To me, this is just a plane with two transverse foliations and a group acting on it. And I stated a theorem of Barbot that says understanding this is enough to completely recover the flow. Okay. Examples of what this thing looks like, I didn't end up getting to. We saw the suspension flow of hyperbolic automorphism of T2 of the torus. This gives as your plane, this is easy to sort of pick out from the definition, what I call the trivial bifoliated plane, which is just R2 with the standard horizontal, vertical and horizontal foliations. Okay. Geodesic flow on the unit tangent bundle of the hyperbolic surface for whichever surface this is and whichever hyperbolic metric, gives you something that is not the trivial plane. Instead, you take, one way to realize this is you take an infinite diagonal strip, okay, and give it the horizontal and vertical foliations. Right. The strip is homeomorphic to the plane, so this is a valid definition of a plane with two transverse foliations. And of course, this is not isomorphic to this one in the sense of there's like a homeomorphism sending foliations to foliations, because here every leaf of one meets every leaf of the other, and here this is just not the case. Okay. Typically, in a sense that's completely not precise, I don't mean anything by typically except that it happens a lot for many examples, you see much more pathological behavior. You'll see branching in the leaf spaces of these foliations. So by a branching leaf, I mean one, so that there's actually another leaf, or maybe many, and a sequence of leaves that limits onto both simultaneously, or maybe all three, or maybe all countably infinitely many. And this will happen also in other directions, and maybe also going up, and also at different scales. So maybe now here's another sequence with many limit points, etc. So typically the leaf spaces of these two foliations are quite complicated. Okay. So this is some example of what we call a bifoliated plane, a plane with two transverse topological one-dimensional foliations, and an action of a discrete group. And it turns out you can recover a lot of the theory of flows from a very abstract definition of this that just captures the most essential properties of this action. Okay. So forgetting three manifolds for the moment, here's a purely abstract definition of an interesting class of dynamical systems. Okay. So I'm going to fix a topological plane with two transverse foliations. Transverse one-dimensional foliations. Okay. And I'm going to say an action of some group G, just the abstract discrete group, on this plane, preserving the foliations, is Anosov-like if the following properties hold. Okay. So first is a kind of the hyperbolicity, maybe in a local sense. So this is the statement that, so I call this hyperbolicity. You have some hyperbolicity, which means expansion, contraction in transverse directions, roughly. So precisely, I want if some non-trivial element of G fixes a leaf in one of the two foliations, the F plus or F minus. I'm using plus minus just because I need two symbols. Then G fixes a point on this leaf. Actually, a unique point, but that'll be a consequence of what I'm about to say. Okay. And the action on the two leaves through L, so here's my, I don't know, maybe here's my leaf L. Here's the point X, the unique fixed point. The action is, up to switching G with G inverse, the action is expansive, topologically expansive on L, and topologically contracting on the other leaf through X. Okay, so there's also a leaf of my transverse foliation through X, and the dynamics is globally, under iteration I expand, hence unique fixed point, and under iteration of the other I contract. Okay. So on the other leaf of X, it's contracting, or vice versa. Okay, so in summary, if there's a fixed leaf, then you get this picture. Okay. Second point is I want hyperbolicity to happen all over the place. All right, so this is some hyperbolicity everywhere. More precisely, the union, if I take the union of all leaves, so of one foliation, so L and F plus, say, such that this picture happens, there exists some non-trivial G that fixes the leaf, that preserves the leaf. Okay, so I take the union of all of these leaves. That's a dense subset of the plane. Mm-hmm. And the same thing, so a dense set of the plane lies on leaves that are fixed by some element. And the same thing should be true if I replace F plus with F minus. Same for the other foliation. Okay. And there's a third property which says that interesting features are also detected by this behavior. So if I have a branching leaf, as I was saying before, one that is accumulated by a sequence of leaves that also has a different limit. So if G in one of my foliations, sorry, L, L in say F plus is branching, this just means it's like a non-Hausdorff point of the leaf space of that foliation, or F minus. Then, also, what's a surprise, there exists some non-trivial element of the group that fixes or preserves this leaf. Those are the axioms. If you like pseudo-Anosov type behavior, so if you want to allow your foliations to have isolated prong singularities, meaning instead of just being transverse foliations, you allow some, I'll draw a 3-prong, you allow some k prongs for k at least 3. So that's a singular point of one of them. Local neighborhood should look like this of the pair. Okay, then along with the spirit of 3, you should add 4, which is that each one of these singular points is fixed by a non-trivial element of G. So a singularity. There we go. And expanding, contracting behaves in exactly the same way. The singular leaf has some prongs. I should say that it's contracting on one of these leaves through this fixed point and expansive on the other. Just like the standard model of a pseudo-Anosov homeomorphism of a surface. Okay, but I will mostly not talk about things with singularities just to keep things short. Okay, definition, here is an interesting class of dynamical systems, groups that act on bifoliated planes with Anosov-like dynamics. Based on this whole motivation, maybe it's no surprise, here's a theorem. If phi is an Anosov flow on a compact 3-manifold, and in fact also on many examples for non-compact 3-manifolds, but not all, then the induced action of G being the fundamental group of the 3-manifold on the orbit space of this flow is Anosov-like. And I can add pseudo if you like the prong generalization too. Let me sketch, well, I'll tell you why the first property is satisfied and the theorems that give you the next 2 properties. Okay. So this is just justifying the fact that I said, hello, we have now abstracted the essential properties of the dynamics of this group action on the orbit space. All right, and indeed, these are properties of this class of examples. Okay, so sum of the proof. Okay, or some remarks on the proof. So what do I have to do for the first thing? What does it mean for an element of the fundamental group to fix one of these leaves in the orbit space? So if G in pi 1m fixes L leaf of, say, I don't know, the stable foliation, maybe without loss of generality, I'll pretend it was the stable foliation. What does that mean? This was induced from the stable foliation in the universal cover of my 3-manifold, right? That means that the corresponding leaf of the lifted foliation in the universal cover of the 3-manifold is stabilized by some element of the fundamental group acting by deck transformations. Okay. So this projects to some leaf in the original 3-manifold with a non-trivial fundamental group. So this projects to a cylinder leaf in the original 3-manifold. So the idea, the picture to have in mind is that here is my L leaf, maybe I'll call this one L, sitting in the universal cover of my 3-manifold. It's foliated by orbits nicely that converge going forward. I picked a stable leaf. And this is invariant under some G, so when I look downstairs in M, it rolls up into some cylinder. And the type of arguments we were doing last time using Novikov's or Haefliger's theorem says that, in fact, there is a periodic orbit here that represents the core curve, the fundamental group of this cylinder, and the other ones spiral onto it. Okay. So we saw last time that G, this deck transformation, or the fundamental group of the cylinder, up to choosing the right base point, is represented by, so I guess technically I should say that the class of G is freely homotopic to a periodic orbit of the flow. Cylindrical leaves actually have a genuine periodic orbit. If I have none, well, I could take a curve that was transverse to all of them, and this contradicts Novikov because the orbits are the other foliation meeting this one. That type of argument. Okay, and this gives me what I want, because now actually the action of G is not just fixing this leaf, but it's fixing an orbit. I don't know what, maybe I can color it something. Right. The fact that this loop closes up means that my deck transformation G is actually translating along a particular orbit. So this is now a G invariant orbit, which means that in the orbit space where each of these orbits is just a point, I can collapse this down in a different direction. My leaf becomes a line, my orbits become points, and I have a fixed point for G. All right. And now what are the local dynamics of this, or the global dynamics of this action? I need to say that up to switching G with G inverse, it's say contracting or whatever. It's either contracting or expanding. So let's see what happens if G is translating along this way, and I take a transverse segment in my leaf. This represents some intervals worth of orbits. G is a deck transformation, and the universal cover is acting by isometries. Right, so this interval gets moved along to an interval of the same length if I'm going in this direction in a stable leaf. And so it's meeting many, many, many more orbits in this stable leaf than it was before. So here's my little transverse segment tau. Here's G of tau. And so that tells me that when I apply G to a little segment here, it's getting bigger. Okay. And in fact, little didn't matter. I could have taken any segment, and it'll be translated by an isometry, and hence meet more orbits, so represent a bigger piece of the orbit space. All right. That's what gives me this global expansive dynamics. If G had been oriented in the other way, then I would get contraction. All right. That's almost all of the statement, except for what happens on the other leaf through X to this fixed point. So here I have my orbit. I have some leaf of a transverse foliation also going through it. Oh dear, there's a transverse plane. And here I have, if that was a stable leaf, this is now an unstable leaf. So if I take the same orientation as I go forward, now leaves are going to diverge. Okay, and so running that same logic of a small segment, now I translate by an isometry, I meet fewer orbits, will tell me that globally the dynamics here are contracting. And that's all the statements that we wanted to show. This is actually a proof of one, and along the way, we saw that what's a nice important fact here is that observation, right, that elements of pi1, which are freely homotopic to periodic orbits, are exactly those that are acting on the orbit space with fixed points. Okay. So I wrote lots of sentences. I mean, I wrote very few sentences and drew a lot of picture. So I'll say here is picture of dynamics. And the key property we used is the divergence convergence of orbits and the fact that that deck transformations are acting by isometries. That's really all we had to use there. Okay, property 2, I will not prove. This follows with a bit of a technical argument from the Anosov closing lemma. Which you can even do in a pseudo-Anosov version good enough to make this statement true for pseudo-Anosov flows. The Anosov closing lemma is going to let you find, if you take an orbit that wasn't a leaf already not on a periodic, an orbit that's not on one of these fixed leaves, well, it's not periodic, so it'll accumulate somewhere, and you use the closing lemma to find a nearby periodic orbit, and you keep track of your epsilons and deltas to get this density type statement. Okay. So that's something I'm happy to explain after if someone is into this kind of dynamics. And the third statement, so this is in some sense classical. And the third statement is non-classical, but this is a theorem of Sergio Fenley in a paper from, I think, 1998. And it's just sort of a remarkably deep observation, or remarkably useful deep observation. I guess that means theorem, right? A remarkably useful result about the structure of branching leaves in stable and unstable foliations of pseudo-Anosov flows. So in summary, here are some easy to state axioms that pick out a class of dynamical systems, of groups acting on the plane, which by this theorem includes at least all of the examples of, that come from Anosov flows on 3 manifolds. I can't resist stating, here's an over-optimistic conjecture that Thomas Barthelmé and I have been thinking about, and I guess we conjecture it because we have ideas which may or may not work to completely prove it. We'll find out. It's the following statement, that these are actually almost good enough to characterize all such actions. So the current state of the optimistic conjecture is that if G acts on some bifoliated plane in an Anosov-like way, and no, say, Z cross Z subgroup of G acts freely, so without any fixed points, then G is the fundamental group of a 3-manifold, which might be possibly not compact, but that it admits an Anosov flow. So I guess a pseudo, if you like. And this action up to conjugacy, that's all it's defined up to. I guess P is the orbit space, and the action is the induced one. So stay tuned. In a couple years, we'll find out if the conjecture is actually true, or maybe you even want to work on it, all the better. Okay, but the general question I want to address today, which I think is actually really interesting, generally. Yes? Nope. Nope. Yeah. I think you should get this for free. For instance, so things we can already say, even without this extra assumption, is like, for instance, that you have all this setup, like the stabilizer of any point is cyclic, virtually cyclic, I guess, if you could be like a Z cross Z2 or something. If you preserve transversal orientations, it's cyclic. So lots of things that resemble the structure of the types of three manifolds and foliations you get in this setting happen just out of the dynamics of these axioms. The general question sort of for this bunch of talks, or for this, and the next part of the mini course is something I think is, whether this is true or not, here's something that's independently interesting. This is the question of how does this kind of Anosov-like action constrain the structure of the bifoliation that I have on the plane. So suppose I have a plane that admits, a bifoliated plane that admits an Anosov-like action of some group. Can it be any bifoliated plane? No, it's very constrained. How does this constrain the algebraic structure of the group G that's acting, right? And vice versa, assuming G acts Anosov-like, how does the algebraic structure of the group constrain the dynamics of action, given that you're Anosov-like and structure of foliations? And I guess maybe I should have made a big triangle, right? You can also ask how does the structure of the foliations constrain like the algebraic structure of G and the dynamics and all of this. These are all very richly related, right? I gave some examples of bifoliated planes, right? A recipe to make a whole ton of examples is the following, right? If you think, if you want to have more creative examples at hand, you could take like any open subset. Well, let's start with an open, simply connected subset of R2. And you could give it the horizontal, vertical foliations, right? And open connected, simply connected, that's the plane in there. And you've made an example. And very, very, very few of these types of examples admit Anosov-like actions, right? Yes?
I have a question from Steve.
Yes?
Can you identify the handles versus flows in terms of the planar action?
Maybe, can you hear
Yes.
me?
Yes. Yeah. Do you want to say more of the question? Mm-hmm.
I'm going to ask a question. If you use your planar action,
Yep.
there's these classes of examples, things like the contact Anosov flows,
Yes.
or the Ferguson surgery flows.
Yes.
Can you identify them? Is that part of the lecture coming up?
It's not part of the lecture coming up, but we can say what many known examples look like. But I won't do that here because that'll take some time. And you need to already know what these flows are, and not everyone does. But I'm happy to talk to you sometime. This is cool. But also, not everything, right? Like, if you give me some generalized Handel-Thurston surgery, I can tell you some features that you will see in this plane. And Barbot's theorem says that the plane contains complete information, but giving a totally explicit description is very tricky. But for large families of examples, we can tell you exactly what it looks like. So, yeah, it's rich, it's interesting, it's complicated. We should talk more about it. Where was I? Oh yeah, for interesting families of examples. So one place I will go with this by the end of tomorrow is I hope to prove a theorem that was proved for Anosov flows by Barbot and Fenley that says, in their setting for orbit space actions, either your plane is one of those two examples like I drew, the one that comes from geodesic flow or the one that comes from like a trivial suspension flow, or both leaf spaces have branching in both directions. Both have two-sided branching. And we'll prove that not using three manifolds and flows, but actually show that if you have a bifoliated plane with an Anosov-like action, then this statement holds. Either the plane looks like, well, it looks like one of the three classes I drew above. Okay. But to do that, we need to build up some background first. And perhaps as by way of advertisement, I'll just announce a couple of results in this direction that I won't prove. So here's some sample theorems towards answers. So here's something about the dynamics, a statement about the dynamics constraining the structure, algebraic structure of the group. So if G has an Anosov-like action that is not transitive, so in the flows setting, these come from non-transitive Anosov flows. But here non-transitive just means, well, here transitive just means that for the action on the plane, there's a dense orbit. Right? So if that is not true, then G contains Z cross Z subgroup. This is something that's done in work with Thomas Barthelmé and Christian Bonatti. A very recent paper on the archive last month. So this mirrors the fact for the result for flows, which you have to prove so far using sort of basic sets and separating tori and Lyapunov functions for this, but we do it just purely topologically in the plane. That on hyperbolic three manifolds, all Anosov flows are transitive. We can also show, maybe here's a one that goes in the opposite direction. If G has a non-trivial abelian normal subgroup, and acts Anosov-like on some plane, then the plane is either the trivial one, in which case G is virtually solvable, or maybe I can even just say solvable here, and the action is act affine, or the plane is the diagonal strip picture, and this non-trivial abelian normal subgroup is actually acting by translation freely along this strip. And if you knew some more things, like G happened to be the fundamental group of three manifold, you could conclude from this that actually the three manifold was a fiber-wise cover of a unit tangent bundle, and the flow that you got from if this came from an orbit space was actually up to orbit equivalence geodesic flow. So this recovers from this perspective a version here of a theorem of Plant about rigidity of Anosov flows on three manifolds with solvable fundamental group, and the results of Ghys on rigidity of Anosov flows on Seifert fibered spaces. You can translate this back up. Okay. So that's the kind of constraints that you get purely out of this axiomatic framework. Okay, so let's, towards doing not quite this, but related, but toolkits towards proving these kind of things or into understanding this relationship generally, let's talk about some background on the structure of these foliations. Okay. So a first observation I didn't prove it, but you can prove it in the margin of your notes right now if you want, is the observation that, I'm given, here's my standing assumption for the rest of time, plane with two transverse singulators, non-singular I think I want, just to keep things simple, foliations. And I won't use it for the next 1 minute, but after that I will want Anosov-like action. Okay. So for my first observation just about the plane itself was that if every leaf of one foliation meets every leaf of the other, well, let's say every, just to make this an easy exercise. Okay. Then your plane as a bifoliated plane is the trivial one, isomorphic to R2 with the standard coordinate foliations. Okay. And if that doesn't happen, otherwise, well, some leaves don't intersect each other, okay? And a way of capturing this is the following definition, first used by both, I think, Barbot and Fenley around the same time, called a perfect fit. Okay, so here's a definition that will be very key for us to understanding structures of foliations. So two leaves, one in each foliation, are said to make a perfect fit. Okay. If they don't intersect, but they almost intersect. Okay, what does almost intersect mean? But here's a slick way of saying this. Any neighborhood of L plus in the leaf space. I need notation for leaf space. I like lambda of F plus. So this is the space of all leaves, the quotient space, if you like. Contains a leaf that intersects L minus. Okay. And vice versa. I'm lazy with writing, so. And any neighborhood of L minus in its leaf space contains a leaf intersecting L plus. You don't get the and for free. You do get it if you have an Anosov-like action, but not for free with work. Right? In general, you could take my recipe over there, like cut out an open subset and do something like, I hope I get this right. Take some chunk of the plane that looks like this somewhere and give a horizontal vertical foliation. Here's horizontal, here's vertical. And so if I look at, say, this leaf here, all right, it satisfies one direction of making a perfect fit. If I look at, this is the pair I'm looking at. If I look at a neighborhood of this one in the leaf space, well, it contains leaves that meet that one. But if I look at a neighborhood of this one in the leaf space, it does not contain, a small neighborhood does not contain leaves that meet that one. All right, so hence specifying both of these actually is adding to the definition. Okay, but warning, this type of behavior where you have one but not the other never happens in the presence of an Anosov-like action. Okay. So this is not the picture of a perfect fit. The picture of a perfect fit is something like, I have two leaves, they don't meet, this is somehow like over at infinity of my plane, but if I take nearby ones, they absolutely do. Okay. This could be the end of my plane, or maybe I could see branching leaves that's either of these is permitted. So. Okay, here's a proposition that I always think is a great warm-up as you start to deal with these objects, and to say, how does the presence of an Anosov-like action constrain what these foliations look like? So let me, in case I run out of space, let's just start on this board. I never know how much space things take. So proposition, our first little warm-up of how Anosov-like constrains foliations. Suppose that I have two leaves that make a perfect fit. And I have an Anosov-like action, and one of these leaves is fixed by a non-trivial element of G. Let's say L plus. G is not the identity. All right, well then, some things I'm going to get for free. So let me write this part for free, and we'll remember we don't have to prove it. Point 1 says that there exists a fixed point for G on L plus. Okay, so I'm going to name this X. Okay, something we do have to prove is that I claim that G also fixes the leaf L minus. And so, of course, property 1 also tells me that there's some fixed point, I don't know why, of G on L minus. All right, that's an axiom. And so encoding this in a picture, I have my L plus, I have my perfect fit with L minus, I have some point fixed by G, and the dynamics are like this, up to switching with the inverse. I have another point here, which is fixed by G, a unique fixed point. And I can look at the other leaves through these two fixed points. Right? And the conclusion is, this pair also makes a perfect fit. Right? So that's what this proposition is really about. And so let's see, that's the minus foliation leaf through X, and the plus foliation leaf through Y, these two, these also make a perfect fit. So a perfect fit plus a fixed point gives me another one. Okay. Let's prove this. Half of it is already done. So I have L plus, I have my point X, and I need to show next that this leaf L minus is fixed. I'll keep the statement. So far I just have this type of dynamics. So definition of perfect fit says that if I take leaf, so let's forget L minus for the second, and let's look at some leaf, oh no, I need another letter, I don't know, little f or something for phi, that passes through that passes through this leaf L plus on the side of the fixed point where L minus lives. Right? This leaf cuts the plane in half, takes something on the half where I was seeing L minus. Right? If I iterate f under G, the power that's expansive in this direction, I'll get a sequence of leaves that accumulates to something. It doesn't go off to infinity because L minus is preventing me from leaving every compact set. This will accumulate to either a leaf or a union of leaves that includes L minus. So to write this, G to the n of f is a sequence of leaves, and this limits to a leaf, or if this leaf was at a non-Hausdorff branching point, or union of leaves in as a sequence that converges to something in the leaf space of L minus, sorry, F minus. Okay. All right, so what could happen a priori is that there's some big sequence like this that it accumulates onto. Okay. But I already know that there is a leaf here that makes a perfect fit. Here I'm going to not be completely pedantic, I'm going to be slightly sloppy and ask you to fill in the details. I claim that the perfect fitting leaf, because it has the property that neighborhoods of leaves that pass through it limit on, leaves that pass through it limit on to L plus. The other direction of every neighborhood of L plus in the leaf space contains something that intersects it. L minus has to actually be a closest leaf. I couldn't have had something like L minus down here and then some other leaves in the limit in between. Right? If not, this will break the property of perfect fit where every neighborhood of this one contains leaves that go through L minus. Okay? So in fact, L minus is, if not the unique leaf, it is the one closest in some, take a transversal that passes through all of these copies, the one closest to L. Okay. So L minus making perfect fit implies that, well, I guess what I should have said a minute ago is that this limit collection as a collection is always going to be unvariant under G. It's a limiting object of the dynamics of G. And what I need to worry about is if there were many things in it beside L minus and if they were non-trivially permuted. But the fact that L minus is closest to this invariant leaf by G tells me that it must be itself invariant. So this is in the limit and itself fixed by G. Okay, so this is an accurate drawing now of L minus here at the edge of this picture. Okay, so already for free here, now I have a fixed point coming from axiom 1. I think I'm only ever going to use axiom 1 in this entire proof, not the other ones. So here's y, and I look at the leaf through it. So I can erase some of this extra scratch work from my picture. F is not needed anymore. That was just to get me the proof that I wanted. Here's L minus, I have y, a fixed point for the action of G, and I have a leaf through it. So my next assertion, well, I'm supposed to show it makes a perfect fit with this red leaf through X. All right. Okay, so there's two things to check. One is that they don't intersect. If these two leaves did intersect, well, this leaf is invariant by G. This leaf is invariant by G. Well, I have transverse foliations. They can meet at most one point, so that point has to be fixed by G. This is bad because G is supposed to have globally expansive or contracting dynamics, so this point is supposed to move under iteration, not be fixed. Okay. So axiom property 1 in the definition again implies that what was I calling this? The minus leaf through X and the plus leaf through Y don't intersect. Is the empty set. So this cannot happen. Now we have an extra fixed point. I have a unique fixed point in each leaf. All right, and now I need this neighborhoods property again. And this I get, again, by iterating the dynamics. So for instance, to check that this leaf is accumulated on by leaves that meet this one, the plus one. Well, here, how about I take in a different color, so my drawing doesn't get too bad, some leaf here. Here's a new F, let's call it F prime. And I can iterate it under G inverse. As I iterate, it's going to approach X. So that means as a leaf, it approaches this red leaf in the leaf space. g to the minus big N of f prime. But of course, it's at the beginning, it intersects this g invariant leaf. So at all times, it intersects this g invariant leaf, the one I awkwardly called f plus of y. So it's also at all times intersects f plus of y, which is half the definition of making a perfect fit. This leaf is accumulated on by ones that intersect f plus of y. And my picture is completely symmetric, so it works in the other direction too. All right, so here's the picture for why they make a perfect fit. Half of it, and then symmetry is the other half. Okay. I like to do this argument because that's the kind of chasing around that you do to prove many of the other statements that I'm now going to assert but not prove. If you can do this backwards and forwards with your eyes closed as a warm-up, and you have a lot of time and willpower, you can prove the other things that I will state, maybe with some hints. Okay, so let's get some board and state two more complicated, let's state, let's maybe just one more level of complication from that. I want to use as a toolkit next time. So, which version of this do I want to do? Yeah, let me make a definition that will be useful. So we came up with this structure of a pair of leaves that make a perfect fit, and then are intersected by two other leaves that also make a perfect fit. So in between, easy to check that this region in between, this open region bounded by these four leaves, is trivially foliated, meaning it looks like a rectangle with the horizontal vertical foliations. And this object is so useful it has a name. So definition, trivially foliated rectangle bounded by leaves making two perfect fits, exactly two. So one perfect fit here, one perfect fit there. Maybe I should specify these are at opposite corners of my rectangle. Okay. So that picture topologically is called lozenge, suggestively by the shape I have drawn as a cartoon on the blackboard. Here's a very powerful proposition that I'm going to not prove, but will use. Okay. So again, I think in this version, it's originally due to Sergio Fenley stated slightly different and about flows rather than Anosov-like actions. And it's the following. So suppose, as always, that I have an Anosov-like action on a bifoliated plane, and I have a couple of branching leaves. I'm going to improve the property 3 to something much stronger. All right. So suppose that two leaves, I don't know, L and L prime in the same foliation are the same at the same branch point, so they're non-separated in the leaf space. They can't be separated by open sets. The sequence of leaves that limits on to both. Okay. The third axiom says that for each one of these, I have some element of my group that fixes it. All right. The assertion here is that actually it's the same. So then there exists a non-trivial element of your group, fixing, not pointwise, but fixing both. And in fact, better than that, these two leaves are related by a finite collection of lozenges. So, and there exist lozenges arranged in the following pattern. So here is L. Here somewhere else is L prime. I see, I guess I've been color coding this. Lozenge here, and a non-separated leaf adjacent to it. This could already be L prime. I'm happy. Sorry, L is this one. This could already be L prime, and I'm happy. Or I might have a larger finite collection, in which case I will see another, let's draw this to look like this, another couple of lozenges. Use the right colors of chalk here. And I get to a third non-separated leaf, and this could be L prime, and I'm happy, or I could have n of these non-separated leaves in between, but always a finite number that eventually terminates. So I don't know, let's pretend my finite number is 1, 2, 3, 4. Here's L prime. With this combinatorial arrangement of lozenges that pairwise share leaves all of the same foliation. So that's not in the plane, that's at infinity. Here, that's not in the plane, and I arrive at L prime. So there exists a finite collection of lozenges, pairwise, sharing sides, arranged in a linear order, so that sides of the extreme ends of them are represented by L and L plus. So, like this picture, also containing L prime as sides of these rectangular regions. All right, so the extreme case is this. Something like this. I have two back-to-back lozenges. And the general case is I could have some finite lined up line of n of them. All right. In particular, iterating an argument like this, all of these are all fixed by G. So every leaf that I have drawn in this picture so far is invariant by the same element of the group. So you get that out of some very clever souped up version of an argument like this, where you consider limits of leaves under iterations and do a bunch of sweat, and you arrive at this much souped up from axiom 3 that says something fixes a branching leaf. You get, any pair of branching leaves are related by a finite collection of them. In particular, any collection of branching leaves in a foliation with an Anosov-like action could be indexed linearly by a set of consecutive integers. A priori, you draw a random foliation, you could have like a Cantor set look, complement of a Cantor set looking like a branching. Okay. So anyway, so this is a powerful structural result that I'll try and use next time to prove a theorem, a classic theorem about Anosov flows, but in the language of Anosov-like actions. But for now, I think we are out of time, so I'll finish here for today.